AP Psych. This is my first lecture I'm filming at school, so we'll see how it goes with, potentially interruptions or announcements, but we're going to give it a go. This is Unit 5, Lecture 3. It's all about storage. So we've learned how all of the memories get encoded or get in here, but then how do they stay here? Later on, we'll worry about how we get them out, but let's just worry about how do they stay here? Like, where do they literally stay? Are there places in our mind that we can point to and say, your memory is there? The answer is yes. This is a little bit more of a technical, one of the more technical lectures in this unit. However, I don't think it'll be too long, so hopefully I can stick to that. Let's take a look. Learning target. Principles that underlie storage. Basic. Here we go. Okay. So the storage basically means retaining that information. So how do we make sure it sticks with us for when we need it later? There are 3 types or stores of memory, and this somewhat mimics the flowchart we had in our first lecture. So we have the information processing model told us that we have a sensory memory, a working or short-term memory, and then a long-term memory. The idea behind this is that something happens in the environment, in our world around us, it goes into our senses, it gets encoded where it's actually, we work with this information and it kind of sticks there. It might even go even further into our long-term memory, but we can retrieve it both from short-term and from long-term. But the majority of information that we retain for later is in our long-term memory. So it's important that we know both how and where our memories are stored. Okay, long-term memory, as we said in the first lecture, is thought to be unlimited. Some estimates range from 1,000 to 1,000,000 billion bits of information. I love that word, 1,000,000 billion. This does not, I don't think that this is literally a number you need to know for class. It's just fascinating if you ask me. And an example of the ability to memorize something huge is this man, Rajan Mahadevan, who actually can recite the first 31,811 digits of pi. Crazy. So long-term storage, pretty basic. It's the idea that we can hold on to an infinite sort of amount of information in our heads. Psychologists and neurosurgeons, or neuroscientists, I guess would be more appropriate, have tried to find evidence that memories physically exist in our brain. As much as we talk about our thoughts just kind of being off into space or being this like metaphorical thing, we know we all have them. And so neuroscientists and neuropsychologists also want to know, but where? Where in the brain can we tell that memories exist? And they call this physical thing an engram. So this is a physical memory trace in the brain. So think of like trace evidence, like what are the bits and pieces that prove that this thing really exists. And they determined that the biological evidence of long-term memories exists in 2 places, in synaptic changes and neural circuitry. And we are going to go into both of those. Okay, the first piece of biological evidence of memories existing in our brain is synaptic changes. What that's referring to is, if we remember, between neurons, there were those little gaps where they don't quite touch, but they come real close to it. And we know from the axon terminal buds to the dendrites, the neurotransmitters shoot out of one and go and are received in the other. In addition to those neurotransmitters, we have enzymes. And these enzymes create chemical traces, almost like a little hopscotch path or like a bunch of stones that you can follow. And those are chemical traces. So the chemical would be these enzymes. And the more you use that memory, the stronger that pathway becomes. If you think of how many times, if you walk through the woods, there's a tall grass, if you continue to walk back and forth on top of that same space, it starts to get beat down, and it's easier and easier to use that path. So it's almost like you're leaving chemical breadcrumbs that can be followed between the synapses. This term long-term potentiation is a little bit more precise to what I am talking about. And here it says, based on recent patterns of activity, synaptic signal transmissions get stronger. That's a fancy way of saying the more you use it, the better or stronger it becomes. In the same way, if you don't use it, you might lose it, referring to that memory. So the more you use that memory, whether you're critically thinking about that thing, whether you're using it on a test or studying it over and over, or rehearsing it, or practicing that skill, if it's like a physical skill with your body, the more you do it, the neuron gets better and faster at firing that action potential. So it can increase the amount of times, or by increasing the amount of times that neuron fires because you're practicing it, or you're using that memory, it's going to get stronger and faster at sending that message. In the same respect, if you don't access a memory for a long, long time, or you're not using it or actively thinking about it, it will fade. If you think of, I think of like my German that I haven't used since my first year of college. I have a couple words here and there, but I don't really remember German. Or if I think about a loved one who passed away some time ago, while I have certain memories, that clear memory of how they sound or what they might smell like or their behaviorisms, some of those things will start to fade. So in the same way that the more you use it, the better you are at that memory, in the same respect, if you stop using a certain memory, it will start to fade. Here's a diagram that I think does a good job of demonstrating what I'm saying. So in a poor memory, let's see if I can bring my mouse over here. In a poor memory, someone with poor memory or a poor memory that's not used very much, there are some enzymes and there are some neurotransmitters that go between neurons, but not many. Meanwhile, when there's a memory that's been used a lot and thought of a lot and practiced a lot, you can see how many more enzymes and neurotransmitters are released. So this becomes faster and easier to do the more the memory is accessed. Okay, the second piece of evidence that we have memories physically in our brain is through the neural circuit system in our brain. So research, this is an instance where we learn more from people with brain damage than we do from studying kind of a healthy mind, just like with Phineas Gage. Research began by looking at individuals who had parts of the brain removed in botched operations. So let me give you a little story here. Henry Molaison, I believe is how you say it, Henry Molaison, who was known as HM in a lot of scientific journals for the sake of anonymity until eventually his name was revealed, had surgery for epileptic seizures, and his hippocampus and amygdala were removed. I think that's the part that was a botched surgery. This was not something that went according to plan. But what happened was he was unable to create new memories of his life, though memories for events prior to surgery remained normal. And so his surgery was in 1953. And so he could remember everything in his life before 1953, but nothing after. He could remember enough in kind of his short-term working memory to maintain conversation, but as soon as he got distracted or that conversation ended, he couldn't retain what had just happened. And the point is that memory exists in specific neural networks of the brain, and that we need certain structures like the hippocampus and amygdala to be able to retain something beyond that instantaneous sensory memory. So what are the parts of the brain that are actually directly involved with memory? In a nutshell, all of them. But there's some specific things that are some specific parts that do specific things. The first one is the prefrontal cortex. So right up here. This is memory involving the sequence of events, but not the event itself. So helping you keep order of a series of events that happens in your prefrontal cortex. Your amygdala encodes and strengthens emotional aspects of memory. In a couple minutes, we're going to talk about why the stronger the emotion, the better the memory. We'll get there. The medial temporal lobe, if we remember, our temporal lobes are right above our ears. It encodes and transfers new explicit memories to our long-term memory, or it's involved in that process. The cerebral cortex, so kind of that overall squishy part of the brain on top, is where the memories become relatively permanent. And we're going to talk about the lobes and the cortexes, which are all part of this in just a second. The hippocampus encodes and transfers new explicit memories to long-term memory. So yes, it does do the same thing as the temporal lobe, but it's two pieces involved in that very complex process. And then the cerebellum, which not only coordinates our body movements and coordination, but it also is involved in the memories of those movements. So in sum, where are our memories stored? There's not one answer. They're all over the brain, with a catch, because there's always a catch. It depends on the type of material being learned, and so the storage location is linked to wherever the information is processed. In itself, that might not make a lot of sense, but with an example, For example, if it's visual information, the memory gets stored eventually in the visual cortex. And if it's like auditory information, the memory gets stored in the auditory cortex, and so on. That's why if we go back to our brain diagram, the cerebral cortex, where memories become relatively permanent, all those cortexes are in the lobes on the outer part of our brain. So if it's like a visual cortex memory and it's a long-term memory, it gets kept in the visual cortex part of the cerebral cortex. How many times can I say cortex in a brief 30 seconds? I don't know. Anyways, that brings me to the last point of this lecture, and that is stress hormones and memory. When you have heightened emotions in a given situation, it makes for stronger memories because your amygdala gets involved. So when you're super happy or super sad or super anything, you are very likely to remember that thing. That's also why flashbulb memories happen. And that level of stress, and yes, even when you're super happy, there's a stress. It's a stress on your body. It's a heightened focus that your mind is in. Stress can boost the activity in your brain's memory forming areas, but if it's continued lengthy stress, it can disrupt your memory as well. So in very emotional situations, we might remember something more vividly than we might otherwise. However, the accuracy of that memory might be flawed because the emotional component kind of blurs some of the finer details. So we will continue to address all of these ideas in class, but that's it for this lecture.